Welcome back to The Explainer. Today, we're diving into the absolute high stakes of maritime computer vision. Just imagine trying to spot a rogue vessel or trying to navigate an autonomous ship through a torrential downpour, all while the ocean waves are constantly scattering your camera's focus. It is easily one of the most notoriously difficult environments for artificial intelligence. But a recent breakthrough study has mapped out exactly how we can solve this, and we're going to break it all down today.
So this brings us to our central question, and really the ultimate feature fight for engineers out there building real-world surveillance systems. How do traditional convolutional neural networks, our trusty CNNs, actually stack up against the newer vision transformers when you put them out on the open water? We're going to look at a head-to-head technical breakdown of these architectures based on recent benchmark data. And honestly, the results fundamentally change how we should be approaching maritime object detection. To really grasp the weight of this research, you've got to look at this number right here. 6,468. That is the massive data set of maritime images researchers used to benchmark these models. And look, this wasn't just some perfectly lit sunny studio test. We're talking dense clouds, blinding fog, heavy rain, and harsh glaring sunlight. It really anchors the credibility of this entire benchmark because it reflects the actual, highly unpredictable conditions a real-world system is going to face out on the waves. Okay, let's dive into this. Here's our roadmap for today. First, we'll establish the Maritime Vision Challenge. Then, we'll benchmark the architectures, look at exactly why vision transformers win, explore the realities of edge versus cloud deployment, and then finish up with a highly practical engineering playbook. Starting off with Section 1, the Maritime Vision Challenge. Before we even touched the code or the models, we have to talk about the sea itself. Out there, the environment is literally your biggest antagonist. The visual obstacles are just relentless. You've got sea clutter, specular reflections bouncing off the water, dense fog, and driving rain. And these harsh factors do something incredibly specific. They severely degrade the local texture cues. Traditional computer vision models absolutely rely on those local textures to figure out, where a wave ends and a boat begins. When the weather turns bad, those cues just vanish. And this quote right from the research hits the nail on the head. Sea clutter, specular reflections, fog, and rain degrade local texture cues that CNNs rely on for feature extraction. Think of it as a micro to macro problem. A localized CNN gets so bogged down staring at the tiny details, like the whitecaps of a single wave, that it gets completely lost in the noise and misses the giant ship sitting right in front of it. Which takes us right into Section 2, benchmarking the architectures. Knowing this massive environmental hurdle, researchers wanted to see exactly which models could actually survive. They systematically evaluated these 6 specific deep learning architectures. They kicked things off with a base CNN, then ran 4 popular transfer learning models: Exception, VGG16, MobileNet V2, and EfficientNet V2L. And then they pitted all those traditional convolutional models against the newer Vision Transformer, or VIT. But hey, it's not just about getting the right answer, it's about how these models perform under serious pressure. The benchmark metrics they looked at included accuracy, type 1 and type 2 errors, model size, and video processing time. And the crucial point here is that these aren't just abstract academic numbers, right? Model size directly dictates your storage and memory limits on a tiny drone, and video processing time literally decides if your system can handle live frame rates for real-time surveillance. Moving on to Section 3, why vision transformers win. Now, what's really fascinating here is the architectural shift that completely solves that spatial scattering problem we talked about. The secret sauce? Global self-attention. Unlike CNNs that look at tiny localized patches of an image one by one, a vision transformer uses global self-attention to process the entire image simultaneously. It completely bypasses the limits of localized receptive fields. So instead of getting confused by the texture of one weird-looking wave, the ViT looks at the whole ocean all at once. This lets it easily distinguish actual vessel structures from all that surrounding sea surface noise. Just look at how this plays out in the data. While models like VGG16 and Exception showed these consistent accuracy drops in low visibility conditions like fog, the Vision Transformer hit an incredible 100% accuracy. 0 performance drop. And not only did it have the lowest error rates, but it also clocked the absolute fastest video processing time across the board. The ViT outperformed the strongest CNN baselines in literally every single metric. So that brings us to Section 4, edge versus cloud deployment. Look, it's really easy to declare a winner at 100% accuracy, but we have to face the harsh practical realities of hardware out in the field.
If you're doing cloud or server-side surveillance, say at a centralized border control hub where you have massive compute power, the VIT is your undisputed champion. But what if you're building an edge or drone-mounted system? You're going to have severe memory limits and really strict inference latency requirements. In that lightweight, resource-constrained scenario, models like MobileNet V2 or EfficientNet V2L become the practical, necessary alternatives, even if they do struggle a bit more in the rain.
And this is where risk framing becomes absolutely vital. In maritime security, a Type 2 error, which means missing a vessel completely, carries a massively higher operational risk than a Type 1 error, which is just a false alarm. If your lightweight edge model misses a detection because of a little fog, that isn't just a statistical blip on a chart. We are talking about a potential border breach or a catastrophic autonomous collision. So, how do we actually mitigate those risks? Let's turn to Section 5, the engineering playbook. This is where we distill all this research into a clear, actionable roadmap for your own production pipelines. Step 1. Adopt VIT for your centralized inference wherever your compute allows. Step 2. If you really have to use CNNs on the edge, quantize them to shrink their size without destroying their accuracy. Step 3. Implement temporal validation. Step 4. Log your performance by weather condition to catch those specific vulnerabilities. And Step 5. Standardize your metrics beyond just accuracy. Keep a really close eye on processing times and error types. I actually want to highlight Step 3 specifically, temporal validation. This is such a brilliant, practical technique. Maritime video feeds are full of transient artifacts, right? A weird splash, a passing bird, a sun reflection. By using a sliding window validator that requires a vessel to be consistently detected across, say, 3 to 5 consecutive frames before it triggers an alert, you can drastically suppress false alarms on your edge CNNs. And the best part, you don't even need to retrain the underlying model to do it. To wrap up our core takeaway for this explainer, the architectural shift from CNNs to vision transformers for maritime computer vision is conclusively proven. It is no longer just theoretical. By processing the entire image simultaneously, VITET has validated its absolute power against weather degradation and sea clutter. It operates faster and way more accurately than those traditional localized models. But, the ocean is vast, and hardware constraints are very real. So I'll leave you with this. How will you balance theoretical accuracy with the harsh operational realities of your next edge deployment? Will you rely on the power of the cloud, or will you optimize for the drone? Thanks so much for joining me for this explainer. Keep learning, keep building, and I'll catch you next time.